Let's explore mass and how it compares to weight. Mass of an object is the quantity of material that makes up the object. Now, one unit of mass that occurs in the SI system is the gram. Right, so gram as an abbreviation would be lowercase g. The gram is defined as the mass contained in 1 cubic centimeter of water at its maximum density. All right, so here's a little picture of a cubic centimeter. So I've got a cube that's 1 centimeter by 1 centimeter by 1 centimeter high. If I were to take that 1 cubic centimeter and I were to fill it with water, right, then the weight of that cube would be 1 gram. Now with all units, it's important to maybe have some real life objects that you can quickly reference when you're thinking about that unit. So some of the other common things that would have a mass of about 1 gram would be your common paper clip or 3 aspirin tablets. Now because your gram is so small, the kilogram is actually the basic unit of mass in the SI system, and it's the only basic unit out of in the SI system that actually has a prefix already attached to it. Now 1 kilogram is defined as the mass contained in 1 cubic decimeter of water at its maximum density. Now remember that a decimeter is 10 centimeters. So the idea is if I have a box that is 10 centimeters long by 10 centimeters wide and then 10 centimeters high, and I were to fill that box with cubes, that is equivalent to 10 times 10 times 10, or 1,000 cubic centimeters, which is equivalent to 1 cubic decimeter. So the box that's formed from that, if I were to fill that box with water, the mass of that box would be 1 kilogram. All right, so if this box was filled with water, its mass is 1 kilogram. A 1 liter bottle of water has a mass of 1 kilogram, so a real life object, so you can kind of figure out what 1 kilogram would look like in the real world. And then 2 NFL footballs together have a mass also about 1 kilogram. Now, for very large quantities, such as a train load of coal or grain or a shipload of ore, the metric ton is used, and a metric ton is exactly 1,000 kilograms. Now, the metric ton, also sometimes it's spelled ton as T-O-N-N-E, or metric ton with ton spelled T-O-N. In the U.S. system, we also have a ton. Sometimes it's referred to as the short ton. And in the U.S. system, that ton is exactly 2,000 U.S. pounds. All right, so the relationship between the metric ton and the U.S. short ton is the metric ton is about 10% bigger. It actually has the metric ton being 2,204.64 U.S. pounds. So if I only had 2,000 pounds, I would be at the U.S. short ton. If I'm a little over the 2,000 pounds, now I'm getting to about the size of that metric ton. And just to make things super confusing, also out there is the imperial ton. Sometimes that's called the long ton. That's a little less commonly seen or used. But there are 3 different measurements in theory out there in the universe where you could hear someone verbally say the phrase ton. And we kind of need to know if they're talking about the metric ton, the U.S. ton, which is also sometimes called the short ton, or the imperial ton, which is also sometimes called the long ton. So those are for very large quantities. The metric ton, again, is 1,000 kilograms. What about for very, very small quantities? So for very, very small masses, we can use the milligram. This is used maybe commonly for like medicine dosages. So some common things that have a mass of 1 milligram is 1 grain of salt has a mass of about 1 milligram. 1 grain of salt. So milligrams aren't very, very big, right? And also, interestingly enough, half of a mosquito has a mass of about 1 milligram. I found that out online. Apparently, one average size mosquito has a mass of 2 milligrams, which means if you cut that mosquito in half, the half of the mosquito has a mass of 1 milligram. So again, very, very small in terms of a unit of measurement. Now, so far we've been talking about mass. We just want to contrast the difference between mass and weight. So the weight of an object is the measure of the Earth's gravitational force or pull acting on the object. The mass of an object is constant. That object's mass will never change regardless of where it is. But the weight can vary depending on the gravitational force. There's actually a formula that relates the two, that the weight of an object is equal to its mass times the acceleration due to gravity. So this is getting a little bit into physics, but just to kind of contrast that in this graphic right here, we have an astronaut that's out in space. So that astronaut's mass is constant. The mass that would be required to make up that astronaut is the same if that astronaut was on Earth, on the space shuttle, or walking around out there in space. But the weight of that astronaut will change. So out there in space, that astronaut then becomes weightless. So while on Earth, that astronaut would maybe have a particular weight. Out in space, now it is weightless. But the mass didn't change. Just in this other graphic that I have right here, here is a box where the box's mass is 10 kilograms in 3 pictures, on Earth, on the moon, and in space. So again, notice that the mass doesn't change. The mass is 10 kilograms regardless. But what's going to change in the different scenarios is the downward force of that box on the actual scale. So on Earth, that box would have a weight of 98 newtons. Okay, remember that mass is measured in grams or kilograms. Weight or force in the metric system is measured in newtons. So the weight of this box on Earth would be 98 newtons. But if I were going to bring that same 10 kilogram box and I would put it on a scale on the moon, that scale, assuming that it hasn't been recalibrated, would show a weight of 16 newtons. So the downward force on that box is obviously a lot less. And if you were out in space, the mass of that box is still 10 kilograms, but the weight of the box is 0 newtons. It would be weightless. All right, so just to kind of as another thing to contrast the difference between mass and weight, we typically would use a balance if we want to find the mass of something, and we would use a scale if we want to measure weight or that downward force. Now, most scales have been calibrated for Earth's gravitational pull, so when you step on them, they actually can show your mass. So they directly measure your weight, and they can indirectly tell you your mass. Mass is measured in the metric system in kilograms. If in the US system, mass is actually measured in slugs. Weight in the metric system, that force is measured in newtons. In the US system, it's measured in pounds. So interestingly enough, pounds in the US system measures weight. Kilograms in the metric system measures mass. So kilograms and pounds is not the kind of the contrasting measurement in one system versus another. To kind of contrast, again, the pounds measures weight, kilograms measures mass. Now, if you have a scale which shows you, when you put an object on your scale, if it shows you what that object is in terms of either grams or kilograms, what is going on in that scale is actually measuring the weight in newtons, and they have a calibration that converts the newtons to its grams or its kilograms. Again, as a reminder, the relationship is that the weight connected to mass is weight is equal to mass times the gravitational pull. gravitational pull. So what happens is the scale actually measures the weight and it does a quick conversion, and then it spits out the mass if it's giving you grams or kilograms as your output.